Hi everyone, my name is Zhehua Zheng from University of Maryland, College Park. Here, I'm going to present our paper titled An Evaluation-Focused Framework for Visualization Recommendation Algorithms. This is a joint work between University of Maryland and Adobe Research. As we all know, visualizations can help analysts analyze data in an intuitive way. For example, visualizing the COVID data can help analysts or policymakers to better understand the case rate, the death rates based on different ages, races, and locations towards making important decisions. However, designing a good visualizations become more and more complicated. We not only need to consider the data size, the data type, but also pick up the appropriate encoding channel for each attribute to be visualized. Moreover, we might also need to personalize the visualization based on the audience characteristic or preference. Therefore, more and more visualization recommendation systems are proposed to the field. The systems take datasets as an input and then output visualizations to help users better understand the data that they are working on. There are some work like Voyager, Foresight, DeepEyes, CDB, etc. have contributed to this research area. The expectation is in the near future, with this technique, anyone could create visualizations for analyzing a new dataset with less or even no visualization expertise. Although many visualization recommendation systems have been proposed to the field, different recommendation algorithms are used in these systems. It is not clear which algorithms should be applied given an analyst scenario. In a review of existing evaluations on visualization recommendation algorithms, we find that many of them are evaluated in isolation. Moreover, some evaluations do not measure users' performance. The visualization community still lacks a consistent framework for evaluating different visualization recommendation algorithms. Some frameworks for visualization recommendation algorithms have been proposed. However, they focus on generating new visualization recommendation algorithms rather than comparing them. Since behavioral difference between the algorithms are not captured through this framework, it is hard to know how different behavioral strategies could impact the algorithm's performance. Given that the purpose of visualization recommendation algorithms is to help analysts visually explore their data, we need a standardized evaluation framework to inform us when and how to apply each of these algorithms effectively. In this paper, we contribute an evaluation framework for visualization recommendation algorithms. We construct the framework aligned with the common recommendation process that the most algorithms follows. We also demonstrate how our framework can be used to theoretically and empirically compare various visualization recommendation algorithms. Based on our investigation, we find that existing visualization recommendation algorithms follow the similar recommendation process. To generate the best recommendations, an algorithm must illuminate the space of all possible visualization designs, and then rank the candidates' visualizations by comparing their utility. Our framework is defined by three major components, which align with the recommendation process. A network represents the space of all possible visualization designs, the traversal method to illuminate candidates' visualizations from the design space. Also an oracle used to compare and rank the value of candidate visualizations. Next, we're going to demonstrate these three components with an actual example. We represent the visualization design space as a network graph, where each node is a group of visualization designs, and edges between nodes represent the operation that changes from one node to another. We use movie datasets as an example. Let's say the current visualization is at node N0, visualizing release date on the x-axis and US growth on the y-axis. The possible operations from node N0 to other nodes could be adding an additional attribute or adding data transformations to current attributes. We use Voyager systems as the demonstration of the traversal method. As shown as the red arrows in the image, Voyager not only illuminate nodes that differed from the current visualizations by at most one attribute or one data transformation, which we called breadth-first search traversal methods. After the illumination step, the visualization recommendation algorithms will need to compare and rank the candidate visualizations, and then select the optimal ones to recommend. Oracles represent the ranking strategies that the algorithm used to calculate and compare the value of each candidate visualization. After the definition and demonstration of our framework, we then talk about how our framework can be used to theoretically compare existing visualization recommendation algorithms. Here, we use the comparisons between different oracles as an example. We can see that different ranking models have different weak points. For example, behavioral models need significant effort to derive knowledge of visualization comparison, while statistic models need to calculate all statistical features of all supported visualizations. And machine learning models require extensive data collection for training the models. Although we can compare the weak points of different oracles, we don't know how they perform in the actual analysis scenarios. Thus, we next demonstrate how our framework can be used to empirically evaluate different recommendation algorithms. Since different visualization recommendation systems have different interface designs, to standardize the evaluation of different algorithms, we use our framework to structure the user studied for evaluating two existing recommendation strategies based on two systems, Voyager and dbounds. We take the oracles, which is the ranking method, from each of these systems. Voyager used CompassQL as the ranking engine, thus we call the oracle of Voyager as CompassQL. The reason we picked CompassQL and dbounds as the texted oracles is because they both are open sourced, and also dbounds is designed on the top of CompassQL. CompassQL focused on recommending effective visualizations, while dbounds not only considered effectiveness, but also the similarity to the reference visualizations. We benchmarked these two oracles to see whether there exists a significant improvement in the user's performance. We then combine these two oracles with two different existing traversal methods, breadth-first search and depth-first search. We use the same interface to test out these four algorithms. Different recommendation algorithms generate different visualizations in the specific wheel C and the related wheel D. We would like to test out the user's performance on various datasets and tasks in the real-life practice. Thus, we benchmark with two datasets and four tasks, including two focus tasks and two open-ended tasks. We recruit 72 participants and utilize between subjects study design. After each task, participants are asked to reflect on their experience using the recommendation tool to complete the task in a short questionnaire. From the benchmark result, we can see that there are actually no significant difference found among texted algorithms in accuracy and time for focus tasks. On the other hand, for open-ended tasks, dbounds exposed more visualization designs than CompassQL oracles. However, we find that significantly more exposure did not lead to more interactions. This finding means that although dbounds exposed more visualization designs, but the exposed visualization might not be interesting enough for a worthwhile data exploration. We also analyzed the post-task questionnaire results. We do not observe any significant difference between both oracles from all 6 ratings. In terms of participant feedback, dbounds generally is preferred as an oracle. Since dbounds take chart similarity into account, it made more sense to the participants when they explore the related wheels. However, we found some comments about the disadvantage for both oracles. In summary, we present an evaluation framework that can describe a large range of visualization recommendation algorithms. We also demonstrate examples of how to use our framework to theoretically and empirically compare various recommendation algorithms. Our benchmark results show that there were no significant difference in terms of users' performance between the two tested oracles, Compascua and dbounds, although participants expressed their preference for dbounds in the post-study surveys. This finding reinforces our motivation that we need a consistent framework to evaluate the benefits of existing recommendation algorithms in the real-world visual analysis scenarios. To develop a better visualization recommendation algorithms, researchers can use our framework as a guideline. Our framework consists of three major components: the visualization design space, the traversal method, and the oracles. While constructing new recommendation algorithms, researchers can think about whether any of the components in the algorithms is new to the community. For example, does my visualization design space contain more meaningful visualization designs than other existing algorithms? Is my algorithm using a different way to traverse the visualization design space, which could help the actual analysis? Is there a new creative ranking strategy that has not been covered by the existing literature yet? Moreover, we also provide a standardized interface for comparing various recommendation algorithms. Researchers can use the interface to conduct experiments to compare their newly proposed algorithms with the existing ones and test out whether their proposed algorithms provide a measurable improvements. Thank you so much for listening to my presentation. If you want to take a look, the paper, the code, and the experiment results are available at the links on the screen. Feel free to ask if you have any questions about our work, or you can also reach out to me by email. Thank you so much.